Let's next discuss the magnetic field due to a current carrying wire. Moving charges are not only affected by magnetic fields, in fact, moving charges create magnetic fields. So magnetic fields only affect moving charges, and only moving charges can create magnetic fields. Very symmetrical. So what we're going to do is we're going to draw the wires in the demo, and we're going to show the direction of current and the direction of the B fields created. Now, note that for the magnetic field created by a single current carrying wire, there are no poles. But as always, magnetic field lines form complete loops.
So I'm going to take my positive end of my battery, I'm going to connect it over here to this end. So the current will be coming out of the screen there. And then I'm going to take my negative end and I'm going to connect it right here. So my current will be going into the screen there. You're going to see these magnets start to move around when I plug this in. Okay, there they go. So here's what we have. You'll notice there is a difference between how these compasses are oriented, where the current is coming out, and again, it's always conventional current's coming out of the screen here, and between these where the current's going into the screen. What is the difference between the alignment of those compi? Aha, where it's coming out of the screen, it's going counterclockwise. Where it's going into the screen, these compasses are all oriented clockwise. So here is the rule. It is called the wire right-hand rule, that if you take your thumb and put it in the direction of the current, which is coming out of the screen here, your fingers will curl in the direction of the magnetic field. Notice the magnetic field makes a complete loop that goes around the wire, which you can't see here. Let me just see if I can focus it so you can just see that wire. Now you can see the wire, but you can't see the compasses. So, Cheng, if you get a shot of this so we can actually see what's going on. It's coming out of the page there and going back into the page there. And so we get called the wire right-hand rule, thumb in direction of conventional current, magnetic field curls around in a circle around the wire. Here, the current's going into the screen, so our magnetic field curls around, in this case, clockwise around the wire. And you may notice, yes, magnetic fields always make complete loops, and this is no exception, but where's the North Pole of this magnet? There is none. When you have just a loop of, you cannot tell where the North Pole is, there is none. For a wire, you don't have a north or south pole, you just have the magnetic field going around the wire in a circle.
So in that demo, here's what we had. We had current coming out of the page on the one part, that's current, and the magnetic field looked like this. Goes around in a circle like that. In contrast, when the current was going into the page like this, the magnetic field was still a circle around that wire, but it pointed in the opposite direction, in this case clockwise. So let's go ahead and write down the equation for the magnetic field caused by a long current carrying wire. Now, officially it's only an infinite wire that does this exactly, but a long wire is, you get pretty accurate results if the wire is long. Here is the equation for the magnetic field due to a long current carrying wire. It is mu naught times the current over 2 pi r, where the B represents the magnetic field in Teslas, and that is the field caused by the wire. I is the current in amperes being carried by the wire. Mu naught, it's a constant. It's exactly 4 pi times 10 to the negative 7. Exactly. And r is the distance from the wire. The B field due to a current carrying wire right-hand rule is the short form. And all you do is you point your thumb in the direction of current, and then your fingers will curl in the direction of the B field. This r is the distance away from the wire, which in this case would be That's the distance r to where you're trying to calculate the magnetic field. Let's go ahead and do an example of this. In this equation, r is the distance from the wire like this. Here's r right there. So notice that here's our wire. The magnetic field goes around in a circle around that wire. And this 2 pi r right here has everything to do with the circumference of that circle is 2 pi r.
So the magnetic field due to an infinite straight current carrying wire is
mu naught I over 2 pi r. Let's do some practice to see if we can just make sure we get the correct direction. What happens if I have a wire like this? Here's my wire, and I've got current going down this way. There's the direction of current. And my question to you is, right here and right here, which is the direction of the magnetic field at those 2 points? Let's go ahead and figure that out. So the wire right-hand rule, your thumb goes in direction of current, so that'll be down like that, and then your fingers curl like the magnetic field. They're going to curl around this wire so that at the left side, which way is the magnetic field over here? Right here, B is into the page, and then out here, right here, B is out of the page. How about right in front? Right here, right in front of this thing, which way is the magnetic field? You notice your fingers are curling. You're looking at the way the tips of your fingers point in front of the wire like this. It's pointing to the left. So right there, the B field is that way. It forms a complete loop. All B field lines form complete loops.
Here's another example of the wire right-hand rule.
If I have current coming out of the page like this, here's I. Which way is the magnetic field around that wire? So it's coming out towards us. Go ahead and figure out the direction of magnetic field around this wire. It will be in a circle using our right-hand rule. And for you guys, so that's this way. And current going this way, thumb goes in direction of current, fingers curl like the magnetic field, so it is counterclockwise. This is the magnetic field right there. And the magnetic field strength here, this is a distance r away from that wire. So the magnetic field right there, it's pointing up, and it's B equals mu naught I over 2 pi r.
One last numerical example.
So let's say we have a wire like this, and let's say it's carrying 5 amperes towards the top of the page. What's the magnetic field 2 meters away? So R right here is 2 meters. What is the magnetic field right there? I'll just put a circle right there. We want to figure it out. Well, we've got to calculate the magnetic field. The magnitude of it is, you just do mu naught I over 2 pi r. And that is 4 pi times 10 to the negative 7 times the current is 5 amperes. You divide that by 2 pi, the radius is 2 meters. And when you get all that, notice that this 4 pi cancels that 4 pi. You just get 5 times 10 to the negative 7
Teslas.
But what's the direction? For that, we have to use the wire right-hand rule or the current carrying wire right-hand rule. You put your thumb in the direction of the current, and then your fingers curl around in the direction of the magnetic field, which over here, where I have my compass pointing, which way will that compass point? Well, that'll point towards you, out of the screen. That's the direction of the B field right there. Direction is that, magnitude is that.